uh, in continuation of the previous my previous presentation on the open loop discrete time system, where I derive all the important formulas that you need to know in order to derive the transfer function of any discrete time system in the Z domain. And as I promised that I'm going to give you another lecture on to explain some of the solution to some of the problems in the book. So now let's first of all look at problem 4.2. And in this problem, if you look at the question, you are asked to find the Z transform of this particular function. This is the function. You are asked to find the Z transform of this function. And in the previous slide, we derive the general equation of finding the Z transform of any open loop system, any open loop discrete system. And we are going to use that formula. We just need to use that formula to solve this problem. Look at the formula here. You see the formula here. AS equals to BS state function of F. So now, to start solving the problem, what you need to do first, you have to write the formula and then compare this formula with the equation. If you compare the formula with the equation, you can see that this BS is 1 over S plus 1, you see, and this F asterisk S, which is the state function of F, is 1 minus epsilon to power of minus TS. Just by mere looking, it looks like it's like that. And why the most important thing here, how do you actually identify, how do you know which one is BS, which one is state function of S from this equation here, from this equation here? How do you know which one is BS and which one is state function of S? The state function of S, as I said in my previous presentation, is actually a function of epsilon to power of TS. So the moment you see any part of the equation with this term, which is actually the Z term, is basically the state function of F. And then the moment you can identify this, you know that the other one should be BS. So now what you need to do here is, this is the general equation to solve the problem, but we need to get the transfer function as I derived in the last presentation. We need to get the transfer function of the function in Z, which is in this form. So first of all, we have to get it in this form. Why we have to get it first in this form is because it is already given in S. When you get it in S, then you can apply the Z transform table and get everything in Z. So now my BS is this, which is clear. I have known my BS now. Then what will be the state function of F? If state function of F equals to 1 minus epsilon to power of minus TS, then you know that Fz, because we need Fz at the end of the day, this is what we are supposed to get the final solution. So Fz, as I said in the previous presentation, Fz is actually the same as the state function of S. The only difference is that wherever you have Z, just replace it by epsilon to power TS. So wherever you have epsilon to power TS, replaced by Z, and that will be your Fz. So looking at this equation, replace this term epsilon to power TS by Z, and then the equation will be this. And then you simplify it. After simplifying, it will be Z minus 1 over Z. So you have gotten your Fz now. What you need to get now is Bz. You already know your Bs. So Bz is a Z transform of Bs. You see, Z transform of Bs. So Bz is equals to the Z transform of Bs. This is Bs. So go to the Z transform table, and from there you can see you will get the Z transform of this directly, without any derivation or anything, and it's going to be in this form. So this is how it's going to be. So this term here that you see is a Z transform of BS. So now you've gotten BZ, you've gotten FZ, so just multiply them and that will be your AZ. That's all. So you have gotten the Z transform of the whole function now. As easy as that. So look at the final solution. Okay, now let's go to the next problem, which is problem 4.3. In this problem, you are given a system in figure 4.2. In the book, it is called 4.2, and this is the figure actually 4.2. This is A, and this is B from the book. So this is 4.2. 4.2 A and B. So you are given this system in figure 4.2 where the input is a unit step function. So the input is a unit step function, which is this. So a unit step function in the time domain, you can write it in the frequency domain, is going to be ES. And so you know how to, if you are given that the input is a unit step function in the time domain, to convert it to the S domain or the frequency domain, you just need to apply the Laplace transform table to get ES from ET. So now, this is the function given. So this is the function given. This is the transfer function given from the question, and this transfer function given from the question is the transfer function of this open loop discrete time system. So now, looking at this open loop discrete time system, you can see that there are about 3 blocks here. The first block is the sampler. So when you have the input ES, you pass it to a sampler, then the output will be the state function of S, which I've said in the previous question. And then this is the zero order hold for data reconstruction, which is basically the digital to analog converter, and this sampler is the analog to digital converter. This is the digital to analog converter, and then this is the plant or the process, and this is the output. So what you need to do, you need to get CS in terms of ES. So O, the transfer function of the system, which is CS over ES. So you need to simplify this. And we know, and we have derived in the previous slide, the transfer function of any system that is similar to this. If you have any system in this form, where you have analog to digital conversion, digital to analog conversion using the zero order hold, and you have the process, the transfer function of this system is going to be CZ equals to GZ times EZ. This is how the transfer function is going to be. So now, by mere looking at this diagram, you can see that, or by looking at this equation of CS, what we need to do, we need to get GZ and EZ. EZ is clear because they said that the input is a unit step. So first of all, you have to get the Z transform of this unit step function. The Z transform of the unit step function from the table, Z transform table, is going to be Z over Z minus 1. This is easy, this is clear. The other one is the false transfer function, which is the product. As we said in the previous slide, this GZ is the false transfer function, which is a product of zero order hold and transfer function of the zero order hold and the transfer function of the plant. So which is this? Look at it. After multiplying the zero order transfer function of the zero order hold and transfer function of the plant, and then you get the Z transform. This one also you can get from the table, because this will be like a constant, and then you get the other one. So it's going to be in this form. So it's going to be in this form. Going to the Z transform table, you will get it in this form. So after getting it in this form, what you need to do is you just need to do what? You go to your GZ now from the table, you go to your EZ. So what you need to do, just multiply the two, multiply GZ and EZ, and then the equation will be in this form. See? So after you got the equation in this form, so it's going to be after factorizing it, simplifying it, is going to be in this form. So this is the Z transform, or is going to be the CZ, which is the output of the output of discrete system, is going to be in this. It is going to be like this. So now, if you want to know the sequence now, supposing you want to know the sequence now from the output is Z, you want to know the sequence. Now, how do you know the sequence from CZ? As I said from the previous slide, what you need to do, previous topics, if you are giving any output of a system, control system in Z, and you are asked to get the sequence, the number sequence from this transfer function, from this output, you need to do, you need to apply different techniques. One technique that we all know is the partial fraction method. So you need to apply the partial fraction technique here, and then you get the inverse Z transform, and then from there you will have the function like this. So after simplifying, I'm sure you are going to have the function, as you know, is going to be like this. This is how it's going to be, because when you apply the inverse Z transform of this one, this will be what? It's a unit, is going to be 1. This is 1, and this one, the inverse of this one from the table, even from clearly from the table, the inverse of this one, of Z over Z minus 1 will be 1. The inverse of Z over Z minus epsilon to power minus t is going to be epsilon to power minus kt. So this is the sequence. So how can you plot this sequence? The way the sequence is represented in this graph here, which is 4.2b. Look at it here. So now if you have at k equals to 0, this will be 0. At k equals to 1, depending on the sampling time, is going to be, the value will be this. So it's going to be an exponential, is going to be this output in 4.2b. You can see that it's rising exponentially to a final value, and the final value will be unity at the sampling instance. You can note that from here that the Z transform analysis yield the response only at the sampling instance, and based on our previous analysis that we did in the previous lecture, we know nothing about the response of the system between the sampling instance, which is clear. So this information is just what we need now, which is also, that is what actually happens in a practical situation, and that is just enough to find the complete EV response of the system. So let's go to the next problem. The next problem is 4.4, and in 4.4, what we are asked to find is that we are asked to determine the step response of the system. This system, look at the system here. The system, we are asked to find the step response of this system. Supposing that the filter is described by difference equation. So this is the difference equation of the filter. This is the filter, which is dz. So the difference equation, which is the output as a function of the output sequence as a function of the input sequence. So this is the equation describing the filter, the operation of the filter. And so from this diagram and with this equation, we can be able to determine the transfer function of this system, which is Cz over Ez in Z. And this is actually the formula. We derived this formula previously in the last presentation. So from this formula now, is very clear. What you need to do is that you need to find each of these terms from this diagram and this equation and just plug them in, and then multiply the three of them, and that will be Cz. So first of all, I need to get, what is the first thing to get is dz. Dz is a transfer function of what? Look at it here. Is a transfer function of the filter, which is mz over ez. You see, mz over ez. So, and mz over ez is going to be like this. And how are you going to get? What is the easiest way to get mz in relation to the relationship between mz and ez? The easiest way to get it is by go to this equation, and then apply z transform to this equation. So if you apply z transform to this equation, the left side mkt, the z transform mkt, as we learned from the previous lecture, is going to be mz. 2 ekt is going to be 2 ez. This one is the sequence, which is the sequence ekt shifted to the right, because this ek minus 1t, it means the sequence shifted to the right. So if it is shifted to the right, and you are getting the z transform of it as we learned from the previous slide, you have to put z to power minus 1. Z to power minus 1 means that the sequence is shifted by one sample period to the right. So it's going to be z to power minus 1 and then ez. So from here now, you take a common factor ez, and then you get mz over ez is this. So if you see this one is the same as this. So after simplifying, so you can see that the easiest way to get the transfer function in z of the of the digital filter is just to get the z transform of this equation, and then from there you will get the z transform of the filter, or the transfer function of the digital filter, which is this one, which is 2 minus z to power minus 1. So you have finished with dz. The next one that you need to get is what? Is dz. This dz, as we said, is a product of the transfer function of the zero order hold and the transfer function of what? Of the plant. So multiply the two of them. You see here, GPS and this is the transfer function, but in S of the zero order hold, and this is the transfer function in S of the plant. So multiply the two of them, and it's going to be like, after multiplying, then you get the Z transform of it. So after multiplying them, don't get the Z transform of each one separately and multiply. This is wrong, as we established from the previous lecture, that if you are multiplying two transfer function in S, you have to multiply them first of all in S, and then you apply the Z transform from the table. You will get this. So now it's very clear now that I have now this one will be my GZ. I know my GZ now, so I need to multiply the three of them now. The first one, DZ, is going to be this. This is DZ, you see, is here. The second one is this one, which is DZ, and the last one is the Z transform of the unit step input. So that's all. You multiply the three of them. So after multiplying the three of them, you will end up with something in this form, and then this you can factorize it further.